Hello students, welcome back. We completed up to section 3. Now let's go to section 4, finite cyclic groups. Before that, however, let's do just one more recap. This time I'll be really brief. Please recall the main theorem of this lesson, theorem 1.5, a subgroup of a cyclic group is cyclic. And here's a summary version. Let A be the generator of the starting cyclic group. And how do you find out the generator of an arbitrary subgroup H? Like this. The smallest positive integer that satisfies A to this power belongs to that target subgroup H. This is a non-empty subset, of Z plus, which is well ordered, so the minimum is well defined. Consequently, m is well defined, so that a to the mth power is well defined. Remember all those? And then we use the division algorithm as the main tool. Yes, we can use the division algorithm because m is a positive integer. So we can divide by m. And then we used pretty much the same argument in 3.1 here when we proved that each power expression of an infinite cyclic group is unique. In other words, they're all distinct. And we used the proof by contradiction, and we set up like this. Pretty much the same. The smallest positive integer, so that a to that power is e. And then we take the minimum of that non-empty subset of Z plus, and that's how we get m. What's the difference? Well, a to the nth power belongs to H versus a to the nth power is E. So this is a restricted version where H is just a trivial subgroup. Otherwise, pretty much the same. And not coincidentally, we're using the same thing, the division algorithm, as the main tool. And then we use this to prove that all infinite cyclic groups are basically isomorphic to Z under the addition. Basically, they're all the same structure. Now let's go to the finite cyclic groups, and we're going to use similar techniques to characterize the order of all finite cyclic groups, and in the end, this is what we're going to prove. They're all isomorphic to one of those Cm, the residue class. So the end result is again very, very simple, but then again, end result may be simple, the proof is not. We have to take appropriate steps. So let's begin. Let's begin from 4.1. Let's begin with a cyclic group with generator A with a finite order m. Then we claim that this order is the very same formula we saw before in 3.1, the smallest positive integer, so that a to n power is e. And of course, we'll have to establish that this is a non-empty subset of Z plus, which is well ordered. So the minimum is well defined, and consequently, we can define m. The key, of course, is whether this is non-empty or not. That's something we'll have to do. And of course, we'll have to use the division algorithm. Similar form, the same idea, same technique. By the way, here's the second half or second part of this. Not second half, let's say 10%, I guess. So a to the nth power, any nth power, so that a to the nth power is e, then m divides n. In other words, n is divisible by m. Again, we are talking about divisibility, so it's got to be the division algorithm that we have to use. As a matter of fact, the final part is left to the students, and then we're going to pay attention to only the first part. But before that, let's make another observation. This one here is actually equivalent to this one down here. What's this all about? Instead of a to the nth power is equal to e, I can separate that a to the nth power into two parts, so that a to the h power is equal to h to the k power. And then instead of just one integer, take the difference between the two, and we claim the difference is strictly positive. And this one and that one are equivalent. That's basically what I'm claiming. And then these two sets are actually the same, so non-empty, so the minimum is well defined, consequently M is well defined. Do you see the equivalence? In case you don't, well, here's a brief explanation. So a to the h power is equal to h to the k power, and then all you have to do is flip this to the other side by dividing it away, multiply by h to the negative k power, because that's the inverse, and we are talking about a group, so inverse always exists. So divide it away, then we get this one here, and that's basically the same as this one up there if I rename n as h minus k. But then again, what if h minus k is negative? I mean, you cannot have 0, by the way. That means h and k are the same, then they're both e, so that's trivial. That's not what we want. So h and k should be non-zero, so it's going to be strictly positive or strictly negative. Strictly positive, then okay, z plus, but strictly negative, well, in that case, without loss of generality, we can assume h is greater. Or you can take absolute value like that. Either way, it'll work out. In any case, please note that this and that are equivalent because of this observation, and because they are the same, I'm using the same color, purple, to denote the same property. So we're going to mix these up because they're equivalent. This one is going to be simpler, so when we define M, we're going to use this. And when you use the property of M, maybe this one is more convenient, and we're going to use that. Okay, ready? Here's a proof, and we'll have to start from M. Yeah, the very same, but there's a bit of a problem, just a little bit of a problem. Is this thing well defined? I mean, z plus is well ordered, so minimum always exists if the set is non-empty. But is it really non-empty? We have to establish that. Otherwise, this expression is totally meaningless. So before this definition, we have to go back and then establish the non-emptiness. So let's go back to step 1, and let's make this observation first. If every a to the n power is unique, if they're all different, then you're going to get an infinite cyclic group. So that's not what we want. We have finite cyclic group, so they are not going to be all unique. In other words, there are two different integers h and k, so that the powers are the same. Or, yeah, like that. Let's rewrite it like this, using symbolic expression. So if everything is unique, they're all distinct, then we have to have an infinite group, but this is finite group. So we have to have a distinct pair of integers h and k, so that a to the h power is equal to a to the k power, purple, or equivalently, like that, subtracting one from the other. And of course, I can assume without loss of generality, h is greater. Is there further explanation? Okay, yeah, further explanation. Multiplying by h to the negative k power to each. Okay, all right, that was simple. So this h minus k exists. Therefore, such n exists. Consequently, this set is non-empty. Yes, we can define the minimum. Okay? If the original cyclic subgroup, original cyclic group G is infinite, then there's no such h minus k. So this whole thing is actually an empty set. So this entire expression is actually meaningless. But for finite cyclic groups, yes, it does make sense, because we do have h minus k like this, which is strictly positive. So that's my n. And consequently, this set is non-empty. So minimum is well defined. So M is well defined. Okay, so much for the preparation. Now the main claim. We claim G can be written like this. A squared, a to the third power, and so on, all the way up to m minus first power. Now, one inclusion is trivial. That's obvious, because A belongs to G. You see G is this one here. Cyclic group generated by A. So A belongs to G. So A to the whatever power belongs to G. So everything here belongs to G. So one inclusion is clear. It's the other inclusion that we have to prove. In other words, if anything, arbitrary element A to the n power belongs to G, then that A to the n power has to be one of these. Some A to the rth power, so that's what we want to prove. So A to the r power, where r is between 0 and n minus 1, so that everything here belongs to this. How do you do that? Well, we use the division algorithm. Arbitrary n and divide by m, and we have this blue and green. M, the dividend, is q times m plus r, the quotient times divisor plus the remainder, and the remainder is greater than or equal to 0 and strictly less than m, the divisor. And then we can do a to the nth power computation like this. Can you read it? Let me expand the font so that you can read it better. So a to the nth power is a to the qm plus r power, as we saw before, and then consequently a to the qm power times a to the r power by the exponent rule, and then a to the n power times q power, a to the r power, and a to the m power, what is it? Well, m is the minimum of this, so it's a member of this set, so it must satisfy this condition. So that's e. So a to the n power is e, so e to the q power, this entire thing is e, so a to the n power is equal to a to the r power, where r is between 0 and m, you see. The remainder is greater than or equal to 0, but strictly less than m, the divisor. So, arbitrary element a to the n power should be one of these. So we prove the other inclusion as well. And then the first inclusion is obvious, so put those two together, we get the equality. And indeed, we just proved the equality. So G is precisely that. Are we through? Did you just prove there are precisely m elements here? Actually, not just yet. We just proved that the order of G is less than or equal to m according to this, as a matter of fact. What if we have a duplicate among those? In that case, everything will break down, so we have to take care of that first. I mean, that's not the first, that's the last obstacle that we have to take care of. We have to prove that each a to the r power in this expression is unique. They're all distinct, so that we have precisely m elements. So, how do you prove that? We'll select two distinct elements, a to the r power and a to the s power. Yeah, two distinct elements from here, greater than or equal to 0, less than m, and they're different. R and s are different. If you subtract one from the other and take absolute value, the biggest will be m minus 1 minus 0, so less than m, yes. And then they are different, so greater than 0. So this integer, r minus s, in absolute value is greater than 0 and less than the minimum, because m is defined like this, you see, over there. And then greater than 0, so it's a positive integer, but it's less than the minimum, so this purple must be false. They have to be different. So they're all distinct. Consequently, the number of elements is precisely m. That completes the proof. So, if you have a finite cyclic group, then that order is obtained by this formula here.